All right, welcome back. Frankly, over the past, I don't know, few days to few weeks, we've been working through a collection of integration techniques. And I think the section that we're focusing on today really gives us an opportunity to step back and look at all that we've done, and then sort of within context, be able to assess, given a particular integral, how might we approach it? Because it is frequently the case when encountering an integral of any kind that maybe one and only one of the techniques that we've seen will lead to finding the appropriate capital F function. And yeah, in a lot of cases, then how do we detect what integration technique to use where? So thinking way back to sort of the first month of our course, we encountered U substitution, and the sort of the tell of a U substitution integral is, in particular, you will have an inside function. That's what we call U. So if there ever is a function inside another function, that's a symbol that maybe U sub is going on. But then you also should be finding the derivative of that U in some form or fashion, maybe scaled by a constant multiple, also as a factor within that functional expression. So that's the standard form of a U subintegral. To see a specific manifestation of this, maybe we could do like integral of 2x cosine x squared. So here's an example where U sub would come into play. The x squared is our inside function, and the 2x is the du over dx that's showing up as a factor. We also had integration by parts. We had sort of three common forms that appeared here. One was if you have an ln x inside your integral, integration by parts is something to at least consider. If you've got an inverse trig function inside your integral, again, integration by parts is something to consider. And then a classic form is where you have a polynomial times either cosine to the kx, sine to the kx, or e to the kx. And so, actually, if you look at this function up above, the 2x times cosine x squared, that's almost of the form polynomial times cosine kx. But to put an integral on the board here that would be of the form of an integration by parts integral, note, only subtly different in expression. Here, integral x squared cosine 5x, but now integration by parts is going to be the tool of choice. When it comes to integration by parts, we've always got to select what is our u, letting everything else within our integral be our dv. And when we have an ln or inverse trig within our integral, the ln or the inverse trig would be our u. And in the case of a polynomial times cosine kx, sine kx, or e to the kx, as we would have here, like the x squared, the u would be x squared. And if we remember from whenever we applied integration by parts in such a situation, the degree 2 polynomial in front of our either cosine, sine, or e, in this case the cosine 5x, would imply that we're going to have to use integration by parts twice over. As far as trig sub goes, when we're talking about trig sub integrals, we have integrals where we have a degree 2 polynomial inside a square root. So an example where trig sub would come into play would if we had like 1 over x squared times the square root of 9 minus x squared dx. So here's an example where trig sub comes into play, and the telltale sign of trig sub is when you have a square root with a degree 2 polynomial inside. So that's a sort of a signal that trig sub comes into play. A nice thing about trig sub is it's relatively straightforward to recognize when trig sub may be in play, and yet the not so nice thing about trig sub is it takes a long time to work through. And yet the techniques of trig sub are quite pleasant in that they do work out and resolve quite effectively, albeit through a lengthy procedure. I will say this, and sort of hinting to something I'm about to discuss, like just because you see a degree 2 polynomial inside a square root doesn't necessarily mean that you're using trig sub. So let me go up here to an example of a u sub integral. What if we had integral of, let's say, x times square root of 9 minus x squared? If we just naively go about trig sub in a situation like this, I think the trig sub will actually still work, but frankly, it's a lot more work than is required, because if you know here, we do have an inside function. The inside function is just the 9 minus x squared, and the derivative of that inside function, while not exactly appearing, appears as a constant multiple. The derivative of our inside function here would be minus 2x, and of course minus 2x doesn't show up, but it sort of more or less does with just a constant multiple of minus 2 factored out. And so hey, we could apply u sub to this here with u equals 9 minus x squared, and that would work out quite beautifully. So yeah, one of the ideas here when it comes to integration strategy is noting that the fact that we have a form of trig sub, like, or a form of any of these integrals, doesn't necessarily mean that every time you see a degree 2 polynomial inside a square root, you're using trig sub. It just means that if you do see a degree 2 polynomial inside a square root, that's something to consider. What about partial fraction decomposition? Here we have a polynomial over a polynomial. In fact, often the denominator polynomial is factored. So if we had something like integral of x over x minus 2 x plus 3 dx, here's a classic form of a partial fraction decomposition integral, and yet just because we have a polynomial over a polynomial like we do in this case doesn't mean that we necessarily are using partial fraction decomposition. If I may, to provide us another u sub example, what if we have integral of, let's say, x squared plus x over 2x plus 1 dx? So here's an alternative example, which indeed is a polynomial over a polynomial, and yet this polynomial over a polynomial, while you could use partial fraction decomposition, it would work perfectly fine. That would be an unnecessarily lengthy procedure for this integral because, check it out, the numerator is just the derivative of the denominator, and so we could apply u sub in this case with u equals x squared plus x. And so maybe one of the themes that starts showing up here in this section is the classical forms of integration by parts, trig sub, and partial fraction decomposition, while sort of telltale in their form, can also have expressions where u sub would apply. And if u sub does apply, it's almost always easier than the other techniques. And so what I'll do, I'll wipe the slate clean here and just throw up a few examples where we can see an integral that would take the form of integration by parts, trig sub, or partial fraction decomposition, but really u sub is the better tool of choice. All right, so here are a few sort of juxtapositions, if you will, to see integrals that are like nearly of a similar form, and yet different techniques would apply. So here are two integrals that include an ln x. Now, generally, when you see an ln x in an integral, we're thinking integration by parts is a possibility. However, in one of these two cases, u sub is preferable. So if you want to sort of pause the video, maybe think about it, which of these two integrals might u sub be preferential for? So as far as where u sub is more preferential, this one on the right would work nicely with u sub. If we use u sub here with u equal ln x, note that the derivative of u, du over dx, is just 1 over x. And well, that's preferential, right? Because the 1 over x is hanging out within our expression. So to sort of manipulate using u substitution, we could ultimately take this integral and write it as just u squared du, which is, well, hey, not bad at all to work with. So u sub is the tool of choice in this case, whereas in the other case, boy, u sub wouldn't work. If you tried to let u be x squared, you'd be running into issues because the derivative of u is only showing up inside the ln function, which really isn't helping us out. We want the u to be inside another function, not the du. And so, right, as we would go here, we would apply integration by parts with u equal ln x and dv equal to x squared dx. And then we'd go through the process and procedure of integration by parts in that situation. Take this second dot point here. So now we've got the integral x over square root x squared minus 16 and the integral x squared over square root x squared. Oh, I wanted this to be minus 16, but just so it looks just like the other. And I claim one of these, u sub, is friendly, and the other, we would have to use trig sub. So maybe pause the video, think it through about which of these two integrals might work, u sub or trig sub. Right, and upon reflection, the first integral here would be our u sub integral. So we'd use u sub here. And why is this? Because inside our square root could be our u equals x squared minus 16. And if u is x squared over 16, then du over dx is just 2x, which means, well, the x that we have would just be a half of du over dx dividing by 2. And that means that you could take this entire integral using the u sub and write it as, let's see, the u would be to the minus 1/2 power because it's downstairs. We have that 1/2 multiplier, and hey, that's just an application of the power rule. So this is a really nice form for u sub, and when you compare that to the arduous process of trig sub over here, where we'd have to start with what x equals 4 secant theta, boy, we've got a lot more work ahead of us here in this integral on the right. And while certainly you can use trig sub in the integral that's on the left, boy, why use trig sub if you don't have to, kind of thing. And maybe that's one of the ideas when it comes to integration strategy. When you first learned u sub, it seemed like an arduous process, but at this point in the game, u sub is definitely like less arduous than the other procedures that we've seen for integration techniques. So if you can use u sub, my goodness, why not? What about in these last two examples? One of these I claim is a partial fraction decomposition situation, and one of them is not. So, right, maybe pause the video, figure out which one would be more u sub friendly. And as it turns out here, what you notice is on the left side, if you let u be that x squared minus 4, then du over dx is just 2x. And while yes, you don't have a 2x here, you just have an x, that's okay. You could divide both sides by 2 or multiply both sides by 1/2 and get that x appearing. And so via substitution, we could rewrite this integral as well. We'd still have that factor of 1/2, but the u is just hanging out downstairs with the du off to its right. And while, of course, you got to invoke the ln absolute value u in this case, so be it. That's only so terrible in comparison to going through an entire partial fraction decomposition. If we were going through partial fraction decomposition here, our first step might be writing the denominator as x plus 2x minus 2, and then we're sort of off and running there, right? Trying to rewrite this as a over x plus 2 plus b over x minus 2. Right, and then again, well, right, could partial fraction decomposition work for the integral that we had articulated over here on the left? Yes, partial fraction decomposition would still work, but why go down the entire long arduous algebraic process if you don't have to? And so I think the sort of the takeaway here is tune your eyes to each of the forms of the integrals that we utilize whenever we use the trig sub or the partial fraction decomposition or the integration by parts, but also keep your mind open to the possibility that just because something is seemingly overtly of that form, it doesn't necessarily mean that that is the only technique that would apply. And heck, if you can use u sub, my gosh, why not, right? Because it is such a it's such a useful tool whenever it is available. And in that sense, we can think sort of strategically about any integral that we encounter. And I think what makes this section quite powerful in our study is it now allows us to take a step back, look at all these integrals, because let's think ahead to how many weeks and months from now we'll be taking the final. Like we're not going to be told what integration technique to use on what integral. And so when you're just getting 5 integrals to compute the capital F function of on your final exam, which technique to use where, you're going to have to decide. And so getting a familiarity with the entire lay of the land here all at once, I think will be excellent preparation. And well, hey, that sets us up for success by going through this journey.